Hello APCal class, we're continuing on with our 4.3 notes looking at Riemann sums and definite integrals. We left off in example 5, and so with this example they're giving us just some functions, and they're made up of, it should have probably said this, but this is a semicircle, and then we've just got some line segments on our coordinate plane. So pretty easy for geometric areas, and that's kind of what we'll have to use to evaluate some of these definite integrals, but then just understanding, some of the, the reflections, or, just the different transformations, or, if we're taking absolute value of the function, how that affects our definite integral, and, in the area that would go along with these graphs. Okay, so for part A, something to point out again, just to talk about this again, is that the bottom number on your integral is always the starting number. So that should be your smaller number, and then the top number should be your larger number. If that's reversed, there's a property that we use to deal with that. Okay, so from -4 to 0, that's the boundary that we're working with right now. Now there's a smaller yellow graph here, so it's just so that we can do some sketching for each one of these with the different transformations. Now, if you have a negative in front of the function, if you're thinking, what that does to the actual graph, a negative out front, that's a reflection over the x-axis. So it flips everything over the x-axis. So from -4 to 0, which is going to be right here. Okay, so I'm gonna reflect this semicircle. So I'm gonna have this part of the semicircle down here, and then this this line segment, which has a slope of 1/2 because it goes up 1 and over 2, down 1 and over 2. So that's gonna look like that. So the area involved here would just be this part of the semicircle that's below the x-axis. Now remember that implies if it's below the x-axis, the value of the integral is going to be negative. Even though we know that area, area isn't negative, but the value of our definite integral is going to have a negative value, and it's represented as below the x-axis on the graph. Okay, so for this we just want to, we can find our area of this would just be a quarter circle in this case, so it would be 1/4 pi times radius. Now our radius in this circle is 2, so pi times radius squared, so 1/4 pi r squared. And then what we have left, zoom in on this a little bit, so we've just got this triangle with a base of 2 and a height of 1, so the total area for that would just be, it's 1/2 base times height, so 2 times 1 times half, that would just be 1. Okay, so what we have then, like I said, with this negative out here, I could just do my area and then just say everything is going to be the opposite sign. So I could put a negative in front of all of that. So a quarter circle plus the little triangle there, so that would end up just being pi plus 1. But if I negate both of those terms, negative pi minus 1 would be the value of the definite integral if I distribute that minus sign through. Okay. All right, next one. If we throw an absolute value over the function, it's only going to change the part of the graph that's below the x-axis. And so now we're looking from 2 to 6. Okay, so from 2 to 6, starting at 2, we're good, that's positive. And until we get to, it looks like 4, right, 4, that's where it dips down and goes negative for, between 4 and 6. So that's the part that's actually going to get reflected back up. So this part would come back up like this. So that negative part becomes positive, and so the area that we're looking at from 2 to 6 would be this part right here, and now this part right here. Okay. So as I calculate this out, just geometrically, I have, let me zoom in here, so it's one little, this is a square right here, so that's 1, and then it's half of a square, so that's 1 and 1/2. And then what else do I have? I've got a 2 base and a 2 height, so 1/2, 2 times 2, that'd be another 2. So I've got 1.5 here plus another 2. So I've got 1.5 plus 2 for my area would be 3.5 for the value. And it's just, a little bit of geometry. I think you could calculate those areas up right? 1 and then a half, and then this triangle here would be area of 2, so that would be our total there. Okay. All right, these other ones down here, I think I did just leave them worked out. That's okay. Okay, so with this one, we're going from -2 to +1. Now, here's the thing, though. When you have a +2 or a -2, but if it's inside the parentheses, what that means is that there is a horizontal shift. So rather than re-sketching this graph where it's shifted 2 units to the left is actually what this means. The easiest way to probably calculate the definite integral here is to say, well, I'm adding 2 to each of the x coordinates. These are x values on your bounds. So if I add 2 to the bottom bound, I get 0, and if I add 2 to the top bound, I get 3. That way I don't have to, so I can just shift my bounds rather than shifting the graph 2 units to the left, and then I'd still be looking at a shape that looks just like this, except it's shifted 2 units to the left from -2 to 1. We can just say, well, let's just take it as it is, but then let's look at it, if I add 2 to each of those. So it'd be from 0 to 3 as it's sitting, okay? So it's just going to be this little rectangle that's right here. So 3 units in width from 0 to 3, and then the height is 1 across there. So that would just be a value of 3. So hopefully that makes sense. So if you see where inside the parentheses that you've got x plus 2 or x minus 2, that's a horizontal shift. You can apply whatever it's doing to x here in the parentheses to the bounds, which are representing x values, and then just deal with the graph the way it is. Just look at the new bounds that you make, okay? All right, part D. All right, now notice the difference between C and D. In C we had x, the +2 is in the parentheses. Now in this one, it's outside of the parentheses, and this represents a vertical shift, right? Let's write that down. This is a vertical shift when it's outside. This one would have been a horizontal shift. Okay, so with the vertical shift, there's a couple ways we can look at this. There's going to be some properties we look at just below this example. But if it's a vertical shift, we're just going up 2 with the whole thing. And so since we're looking from 0 to 3, this rectangle right here, if I were to take that and shift it up 2, I would just have basically a taller rectangle right there. Now another way that we can look at this is what we're going to see in these properties is that we can evaluate 2 separate integrals here. We can say I'm going to evaluate the integral from 0 to 3 of just f of x, which is our sketch here in yellow, and then I'll add to that the integral from 0 to 3 of just the function 2. Now if we were doing that, just the function 2, I would, that's easy enough. Basically it would just be this. It would be just this shape right here, but it'd be a horizontal line that goes through 2. It would be right there. And then we would add that to what we currently have, which would yield the same thing as if I just kind of look at it, geometrically, shifting the whole thing up 2, and then I just have a larger rectangle up like that. So if I break this apart, 0 to 3 of just this yellow one, again, so we did that before, that's just 3, right? Underneath this right here, this is just... that's just 3 square units right there. And then if I were to do, from 0 to 3 of just 2, right? Let me just do something new. So 1, 2, 3, and then if my function was the function 2, which is just a horizontal line like that, right? Now that's going to end up being 6 square units because it's got a height of 2 and a width of 3, right? So that area in there would be 6. So that'd be 6, and this part here was 3. So we end up with 3 plus 6. So the value of this one is going to be 9. Okay. All right. So some properties. Constant multiple property. So if there's like let's just say the function is 2 times f of x or something, we can take that 2 out and then just and multiply that times our value of our definite integral after we do that piece, and that would be, I guess I didn't see any like that up here yet. We'll have some of that coming up. But here, the additive property. So if you're adding more than one function, you can evaluate each of those separately. Okay. So, and that's kind of what I did in this piece. So we added, from 0 to 3 of f of x, and then plus 0 to 3 of 2, dx or whatever. And so you can just get those values separately and add those together. Okay. and it says definition of two special definite integrals. Okay, so basically what this is saying is if your top and bottom bounds are the same number, well, that means that there's really no horizontal change in your graph, so there couldn't be any area then, if you're thinking of it geometrically. So that would just hit the definite integral. If the top and bottom bounds are the same, its value would have to be 0 because you didn't really move anywhere horizontally on the function, on the x part of it. Okay, and then this one I kind of pointed out before. We need to have the smaller number on bottom and the larger number on top. So if they give you a function that gives you a larger number on the bottom and a smaller number on top, we want to switch those around, but then that switches the value of the definite integral. So then you have to put a negative in front of that. And then finally, if you have pieces, so I kind of just drew this out. So let's say if you have something where C, if C is between A and B, okay, and you're doing the integral from A to B of f of x, but you can break it up because there's like two different shapes or something. That's just saying I can evaluate the integral from A to C, and then I can add to that the value from C to B, like, right there. And so that I can just separate those out and do the individual, if they're shapes usually with, or maybe they've given you information about the value of each of these definite integrals, and then you just add them up as long as it's three closed intervals determined by A, B, and C, like that. Okay. All right. So in example 6, so here we're looking at, it says evaluate this integral from 1 to 3 of f of x plus 6, given that the integral from 1 to 3 of just f of x is 10. Okay, so they give us part of this. So this would be one where we want to break this up and say, okay, from 1 to 3 plus, of just f of x plus from 1 to 3 of just the 6, the second part. Okay, so because they told us this value from 1 to 3 of f of x is 10, so we know that one. And we can evaluate any constant because that's just going to be, our width, it's going to be a rectangle where our width is the distance from A to B, and then our height of our function is just a horizontal line through 6. So it would be, 2 times 6 to give me that value, okay, because, B minus A is going to give you your width, so that's 2, and then times your constant of 6. So 10 plus 12, 22. So that one's pretty straightforward. Okay, part B. So here we've got from -2 to 5, and we've got 3 times f of x minus g of x. Okay, and then they give us some information here. They tell us something about f of x. They tell us that from -2 to 3 of f of x is 6. And then, now this is the other kind of rule that we need to be careful of, bigger number on the bottom. From 5 to 3 of f of x, that integral, definite integral, is 3. So what we want to do with that right away when you see that, switch it around, switch those numbers around, and then give it the opposite value, okay? So, if from 5 to 3 of the integral is 3, then from 3 to 5 it's going to be -3. So we want to use this. We want to do it in order. That way, because we know we want to go from -2 to 5, now we have that. We can go from -2 to 3 is 6, and then we can continue on from 3 to 5 is this value. Then we can add those together. Okay, and then here they tell us about g of x. From -2 to 5, g of x is -4. Okay. All right, so breaking this up. Okay, so first thing, we've got a multiplier, so we're going to take that out. We're going to pull that 3 out in front, and then we're going to do the integral from -2 to 5 of f of x minus the integral from -2 to 5 of g of x. This one we have, they gave us that. That's -4. Okay, so that part I can evaluate right away. All right, but this part right here, this f of x, okay, now I kind of did a little shortcut on this, but because, they told us we have to do this in 2 separate pieces, from -2 to 3, that's 6, and then from 3 to 5 to finish that up, that's going to be -3. So to get the value of this one, it's going to be 6 plus -3, okay, because that's the 2 parts. We're going to go in order from -2 to 3, and then from 3 to 5. So then I can add those together to get this value, which is going to be 3. Okay, then I take 3 times that minus -4, which is going to be +4. So that's 9 plus 4 should give me 13 for that value. All right, and then example 7. Okay, so here, piecewise graph. We want to sketch it out, see what it looks like, and then just work with the areas that we're given. So we're working from 0 to 5. Okay. And for the first part of this line, it's a y-intercept of 7, so I can go up to 7, and a slope of -2, down 2 over 1, down 2 over 1. And I'm going to do that until I get to to 3. 1, 2, 3, because that's where that one's defined. Okay, and that's closed dot there. Okay, that's included. So there's that piece of it. And for the other piece of it, it's just a horizontal line through 4, and that goes from 3 to 5 because that's the top bound there. So for greater than 3, but I'm ending at 5 there, so I'm just going to do, it'll just be that rectangle with a width of 2 and a height of 3, or a height of 4, sorry. 4 is the height there. Okay, so as I calculate this out, I've got this triangle, which is 1, 2, 3, and then 1, 2, 3, 4, 5, 6. Okay, so 3 times 6 times half, that is, 18 times half is 9, but then I've got these 3 more underneath here that I'm going to count out. So this piece right here, which is technically like a trapezoid, but that'll be 12. The top triangle is 9, and then I've got 3 more blocks underneath that, so that would be 12. And then this rectangle is just 2 times 4, so that's 8. So the total there, 12 plus 8, should be 20. Okay, so that's all I'm going to do in this video. We'll finish up with the trapezoidal rule in the last